Okay, we're going to do a couple more examples of the organic chemistry from Wade. So this is from the 8th edition book, doing a couple of different questions, and then the answer that we're going to use is from Wade. So let's say we've got a compound that looks like this. We're going to recognize that we've got a functional group that's an alkyne. We're doing a reaction of an alkyne, and we've got these reagents that are up here. Note that there's two of them, so it's two Br2s. And we're going to go and take a look at what we need to react with. So when we look up reactions of alkenes, reactions of alkynes are right here as well. We'll see that if we were to, for example, here, this is the X refers to a halogen, so it's Br2, Cl2, I2. And if I have two of them and a triple bond, I'm going to get 4 atoms added across the triple bond. And since this, in our case here, we've got Br2, we're going to end up with 4 bromines added across the double bond. So that's what we're going to do. We're going to go back. We're going to go back here and figure out the answer. So I'm going to redraw the molecule. Just note that when I have this compound here with the triple bond, that this is actually linear. I'm just bending it here just so you can actually denote and see the number of carbons, just to make your life easier. But this is a linear structure through the alkyne. So what we're going to do is we've got these two carbons that were associated with the triple bond right here. We know this is where the addition is going to occur. So I'm going to end up with bromine here. So that's the first bromine, Br2, and I'm going to get another one essentially added here like this. So if we're to name this compound, we know we're starting off with a pentane, because I have 1, 2, 3, 4, 5. I'm going to start from this side because we have the bromines closest to this side. If I started from this side, I would have 1, 2, 3 in. On this side, I start 1, 2 in. This gives me the lower numbers, which I'm looking for. And in the 2 and the 2 position, I have a bromo, and then in the 2 and the 3 and the 3 position, I have another bromo. So I have a 2, 2, 3, 3, and now I've got 4 bromines, so I'm going to refer to them as a tetra bromo pentane, all one word, no spaces. Here we have a reaction of an alcohol. So this is a reaction of alcohol, and it's with HCl. I actually found this on page 3 of our document. Essentially what's going to happen here is the alcohol is going to react with the HCl, and it's going to replace the alcohol with the chlorine. So if we were to look this up then, specifically in Wade, we would go through all these, and essentially here we're seeing that if we have a generic alcohol situated here and we've got an acid, so in this case HCl, that we're going to replace the OH group with the chlorine group. So we'll go and take a look at how that is going to happen. So essentially what I'm looking to do then is replace this OH group with the Cl. So I'm going to redraw the molecule here, and as simple as this, I'm going to put in the Cl group. Since we're doing the IUPAC naming, we're trying to find the longest carbon chain, so I'm going to start here with the 1, 2, 3. This is a propane group. In the 2 position is a methyl, and the 2 position is a chloro. So alphabetically, I'm going to say 2 chloro, 2 methyl propane. All one word, no spaces. So we have reaction here. So when we take a look, we'll see that we've got a cyclohexane group here, and we've got a chlorine attached. So this is a reaction of an alkyl halide, and we see that we've got sodium hydroxide as the reagent. So we're going to look. So when we look it up, we can find something similar here. So if I generically have a halogen, and I react it with in this case, a nucleophile like hydroxide ion, I'll be able to replace the chlorine with the hydroxide ion and create an alcohol. So that's what we're going to go ahead and do. So we're going to redraw the cyclohexane because nothing's happened to it. This is the carbon that was attached to the chlorine over here. That's the same carbon. And so what I'm going to do is just draw straight out from here and put the hydroxyl group on. And so that's the substitution reaction that occurs. So to name this compound, this is a cyclohexanol, and I can state that it's in the 1 position. I don't have to because there's nothing on here, but if I wanted to just be complete, I could say it's a 1 cyclohexanol, or I could say a cyclohexan 1 all, or just plain cyclohexanol. Either of those answers would be acceptable. In this reaction, we have another alkyl halide. It's a funny looking molecule, but all I did was just kind of rotate it around. So we start from here, 1, 2, 3, 4. We have a butane molecule. In the 2 position here is a bromo. In the 2 position is a methyl here on this side. Alphabetically, the bromo comes first, so considering that the methyl and the bromo are considered equivalent in terms of priority, so the bromo alphabetically comes first, and so this is the number 2 carbon here. But we're reacting with ammonia in excess, and we're going to see what the outcome of this reaction is. So we go through our resources. Essentially, this is Wade, and we're scrolling down here through Wade, and when we take a look, we can see here that if we have some sort of halogen attached generically to a carbon, and we use excess ammonia, that we're going to replace it and create an amine in that position. So wherever the halogen was, we're going to put an amine in that position. Here's an example of it, where it's an N-propyl bromide, so this is not IUPAC, it's a 1-propyl bromide if it was IUPAC, and we're reacting it with excess ammonia, and ultimately it'll turn into this amine group. It'll be substituted with an amine. So let's apply this chemistry to what we have. So we've got the funny looking molecule here. I'm going to redraw it. And essentially this was where the carbon is that was attached to the bromine, so all I'm going to do is put in an amine functionality here to replace the bromine. So again, we still have 1, 2, 3, 4. We have a butane here. In the 1, 2, we've got an amine, and then up here we will have a methyl group. So in the 1, 2 position is the amine because it's higher priority. In the 3 position, then we have a methyl group. So we're going to end up naming this a 3-methyl propan 2-amine, or I can call this a 3-methyl 2-propanamine. My preference is to bury it inside the name, because when you start to get the much more complicated molecules, this will help you out. In this example, we got an alkyl halide again. We see we're reacting it here with a sodium ethoxide. So we're going to look up how to do this reaction. So generically in Wade, anytime that I have alkyl halide, that just generically there's some carbon attached to a halogen, any nucleophile will attack. And a nucleophile is anything essentially that typically has a negative charge and wants to attack something that is delta positive. So if we scroll down the list here, this is an ethoxide, or in our case here, it can be an ethoxide. We've got the negatively charged oxygen attached to a carbon chain. So generically this could be a long carbon chain, short carbon chain, but in our case it's a 2-carbon chain. And here is our halide, so we have an iodine here and attached to some carbon chain. So generically this is what we're looking for, but we'll try to see if we're going to get a better example of it. But ultimately we're going to create an ether is what it's telling us. So on this page we can see that if we were to have, for example, in this case a methyl iodide and something like sodium ethoxide, that the ethoxide here is going to attack that carbon and it's going to attach and create an ether. So the methyl will be on the one side of the ether and this 2-carbon chain will be on the other side of the ether. So that's what's happening here. Let's take a look at ours and see what's going to happen. So for ours, in the carbon chain is over here, so I'm going to redraw this. This is where the iodine was. The bond was here to the iodine, but now it's going to be replaced with a bond to the oxygen of the ethoxide, and whatever is remaining on the ethoxide is going to carry through as well. And so there's our compound. So as far as the longest carbon chain goes, I've got a 3-carbon chain, so I have a propane. In the 2 position is an ethoxy. So I'm going to call this a 2-ethoxy propane. There are a couple of other ways of naming this. I can go something something ether, and I can also have the oxygen as part of the longest carbon chain. You can go to my other videos on naming ethers to go through those other examples.